In this video, we are going to continue looking at Diels Alder reactions by looking in more detail at stereochemistry considerations we need to make as we predict the products of Diels Alder reactions. The first stereochemistry consideration we will highlight is the fact that in order for a Diels Alder reaction to occur, the diene must be able to adopt an S-cis conformation. In other words, through rotation around the carbon-carbon single bond that bridges the two alkene groups of the diene, we must be able to achieve this conformation. We refer to this as the S-cis conformation, where S means single bond, because of the fact that the two alkene groups here and here are cis to one another. The opposite of that would be the S-trans conformation, which would look, for example, like this, where we would describe this as S-trans, because of the fact that at one of the two carbons of the single bond, S for single bond, the alkene group points up. At the other one, it points down. They're going in opposite directions, so therefore it is trans, versus here in the S-cis, both are pointed toward the right, so therefore it's described as cis rather than trans. Now, generally, if we have an unencumbered, meaning non-sterically hindered, linear, acyclic diene, we can simply rotate around the carbon-carbon bond here in the trans conformation to convert the trans conformation into a cis conformation. However, in the event that the two alkene groups are sterically hindered from easily rotating around, or they're locked into a ring that forces them to be S-trans, those things can slow down the reaction greatly or force the reaction not to work at all. For example, if we were looking at these two alkenes and we were thinking which one would we expect to react faster in a Diels Alder reaction, the structure on the right is going to react faster and be more amenable to Diels Alder. And the reason why is because there's less steric hindrance that would prevent or impede the rotation around the carbon-carbon single bond to transform the S-trans conformation into the S-cis conformation. So this is going to react faster than the Diels Alder because the steric hindrance is minimized for the carbon-carbon bond rotation that is necessary for creating the S-cis conformation. So in both of these cases, they have this S-trans conformation that we're seeing, but in the one on the left, the rotation around this carbon-carbon bond to rotate around and make that group oriented downward like the other alkene group, there's going to be greater hindrance to that happening than in the case at the right, due to the fact there's a methyl group here, a methyl group here that creates steric hindrance. If these methyl groups were even larger, like tert-butyl groups, that would slow things down even more by impeding the free rotation around the carbon-carbon single bond. Now, generally, if we're dealing with these acyclic systems, although the reaction will go relatively slow if there's an S-trans conformation and relatively bulky groups here, because it takes a while for that to rotate around effectively to convert into the cis conformation, there are situations where the reaction can be entirely blocked. For example, if the molecule is literally locked S-trans, that is going to prevent the reaction from occurring entirely. For example, of a scenario where we're locked into an S-trans conformation, we could look at something like this, where we have one alkene group that is in the ring, therefore it's locked into place, and one alkene group outside the ring. These two alkene groups are trans to one another because one of them, relative to the carbon of the single bond, is pointed up. The other one relative to the carbon of single bond is pointed down. So we describe those as being S-trans, and there's no way to rotate around the carbon-carbon single bond right here because of the fact that that bond that I'm pointing to in green is locked into a ring. So that fact that it's locked of that carbon-carbon single bond in a ring totally prevents the S-cis conformer from forming. And hence, no matter what type of dienophile you reacted this diene with, the Diels Alder reaction will not take place because the formation of the 1,4 cycloaddition product, where the carbon at one end of the diene reacts with the dienophile and there's a link to the other end of the diene, would create a structure that was physically impossible, that would be too strained to exist. So when you see situations like this where you recognize that the atoms are locked S-trans, there will be no Diels Alder reaction that can take place there. So don't fall into the trap of looking at reactants, recognizing they're locked S-trans and thinking, oh, they can react because they actually can't. If they're locked into the S-trans conformation because of the fact that, for example, there's a ring that would prevent free rotation here, that is going to result in no Diels Alder reaction. On the flip side, though, on the more optimistic side, if you will, there are situations where reactions will be particularly favorable because of the fact that the atoms are locked S-cis. So, for example, looking at a situation where we're locked S-cis, if we had, say, as our starting structure, a 6-membered ring like so, the two alkene groups here and here, highlighted in gray, are locked S-cis. And so due to the fact that they're locked S-cis, having these locked as S-cis is going to facilitate the reaction. It's going to increase the Diels Alder reaction capabilities of this particular molecule. And this would react faster than a typical diene would, due to the fact that there is no opportunity for that to even rotate into the S-trans conformation. Instead, it's locked, it's trapped as this cis conformation, so it's ready to go in the right conformation rather than having to rely upon free rotation around carbon-carbon bonds to get to that correct conformation. Instead, it's already locked there due to the fact that the atoms are constrained into this ring with those two alkene groups oriented in the same direction. So that's stereochemistry consideration number one in a nutshell, is that absolutely, in order for the reaction to occur, the diene has to be able to adopt an S-cis conformation by rotating around the carbon-carbon single bond. If it's not able to rotate around the carbon-carbon single bond because there's something locking it within a ring, for example, there will be no Diels Alder reaction. On the other hand, if the atoms are locked S-cis due to their position within a ring, that is going to create a really favorable situation for a Diels Alder reaction where the diene would be very reactive to Diels Alder. So now we move on to our second stereochemistry consideration when dealing with Diels Alder reactions. So our first stereochemistry consideration applied to the diene. Now we look at the stereochemistry consideration of the dienophile, and what to keep in mind there is that the stereochemistry of the dienophile is going to be retained. Remember, the dienophile is our alkene. And so what will be the case is that if the two R groups here and here on the diene begin as trans, your Diels Alder product will have those groups trans as well. On the other hand, if the two R groups start off as cis to one another, the stereochemistry configuration there will be retained and they will be cis in the product as well. So that is something to keep in mind, is that when you look at the structure of an alkene, if that alkene can be described as cis or trans, you will need to stereoselectively create the cis or trans orientation of those two groups on the ring when you write out the product. And so as a result, we can describe the Diels Alder reaction as being quite stereoselective. In other words, when we go from the reactant here, specifically the dienophile, to the product. We have a specific preference for the configuration of the product. We're not randomly making a mixture of cis and trans products. Instead, trans starting materials will specifically lead to trans products. Cis dienophile starting materials will specifically lead to cis products. Both work perfectly well in the Diels Alder reaction, and in either case, the stereochemistry is going to be retained. So in this example, we'll apply what we learned in the last couple of points about retaining the configuration of the cis-trans alkene and recognizing that the diene has to be able to adopt an S-cis conformation in order to react. So the first thing to ask yourself when you're thinking about stereochemistry, look at the diene and ask yourself, can it adopt an S-cis conformation by rotating around a carbon-carbon single bond within the molecule? And the answer for this particular example is yes. Even though it starts off as S-trans, we can rotate around the carbon-carbon single bond here, showing that rotation in blue, to rotate this bond and bring that alkene group down so that it is oriented on the same face of the molecule as the other alkene group that it's conjugated to. So we'll get the two alkene groups both pointed downward, like so, or more prudently, perhaps, is to actually rotate it sideways as well so that you can illustrate what's happening in the mechanism more easily. So I'm just putting the equal sign there to indicate that I'm just rotating this on its side. So I just rotated it in the plane of the page, took it 90 degrees that way so that it's now oriented such that it will be facing the dienophile that it's reacting with. I orient the dienophile so that my alkene group is pointed upward. At one end of that alkene group, I put the carboxylic acid group. At the other end, I put the methyl group. And then drawing my electron pushing arrows to show the bonds that are being made here, I take my alkene group from my diene. It comes over, attacks the electron deficient carbon right here. That's electron deficient because it's bonded to the electron withdrawing carboxylic acid group. The pi bond from here has to go somewhere. It comes over and attacks at the fore end of the diene. And then the pi bond here comes over to form the double bond right there. So let's go ahead and draw out the product of this reaction. Plugging in my newly formed bonds in red here just for emphasis. So new bond here, and then we have the two carbons that originate from the alkene of the dienophile connected to the carboxylic acid COOH group, methyl group, and then don't forget that that six-membered ring needs to have a carbon-carbon double bond right here where I've drawn it because we took the pi bond from right here, move that over to make the pi bond here instead. So now thinking about the stereochemistry, the specific location where we need to think about the stereoselectivity of the reaction is here and here. And what will be the case is that at those blue dots, the cis versus trans orientation of those two groups is going to be retained because of the stereoselectivity of this reaction, that when the electrons are flowing in this concerted system, it's going to be happening in a way that the two groups, the two R groups on the alkene, are going to retain their original orientation relative to one another. So trans is going to stay trans. And so since the carboxylic acid group is trans to the methyl group to start with, it has to be trans in the final product as well. So I'll show, to illustrate trans, one of these groups as a wedge, the other one as a dash. And now keep in mind there are two different trans stereoisomers for any particular molecule such as this. And so the other trans molecule would be the enantiomer of what we started with. So change all the wedges to dashes and dashes to wedges as one way of showing that enantiomer. So we will create a mixture of these two compounds circled here that are related to one another as enantiomers, and both would be described as trans. The reaction is stereoselective because in theory, since it has two stereocenters here and here, there could be, theoretically, 4 stereoisomers, 2 cis stereoisomers and 2 trans stereoisomers, but in actuality, we only observe the trans stereoisomers, and so the reaction is stereoselective. So let's now take a look at this reaction where we'll again predict the major organic products. I encourage you to hit pause, try this on your own, and then hit play to see whether you got to the correct answer or not. Just like with the previous example, we have to confirm that we can take our starting diene and convert it into the S-cis conformation. We can indeed do that here because there's nothing locking this S-trans. They are not part of a ring or anything like that. And due to the fact that there are no bulky alkyl groups bonded anywhere, we can pretty easily rotate around this carbon-carbon single bond here in order to transform that S-trans conformer into an S-cis conformer. So I'm going to do that. I'm also going to rotate the molecule around so that the alkene groups are pointed toward the right here so that our terminal at position 1 and position 4 here to show the 1,4 cycloaddition will be oriented toward where I'm going to draw my alkene, the dienophile. So drawing the dienophile, that's this guy right here, just redrawing that so that my alkene group, recognize the alkene group right here, is vertical and lined up for the formation of those carbon-carbon bonds here and here. Got my alkene group in place, drawing the rest of the atoms of this ring, like so. Draw my 2 carbonyl groups in here and here. I'm going to write out the mechanism for this to keep myself on track with where I've formed the bonds. And due to the symmetry that's present here in our dienophile, each of the 2 groups here are equally electron withdrawing because both have a carbonyl directly bonded there and then an oxygen on around the ring. So due to this symmetry and the fact that both of these groups bonded here are equally electron withdrawing, it doesn't matter whether you take the pi bond from here, come over to here, or take the pi bond from down here and attack right here. Either one will work. And so I'm just going to take pi bond from here, come over to here. Pi bond from the dienophile comes to the other end of the diene. Then the double bond of the diene comes down to here to finish off this reaction. And just like we've seen before, we're making a new 6-membered ring, and we are also creating 2 new carbon-carbon bonds to create that 6-membered ring. So our 4 atoms of our diene, I've shown here as the 4 atoms here. 1, 2, 3, 4, 1, 2, 3, 4. Double bond, going to be going right here. And then we additionally need to make those new carbon-carbon bonds over to here and here. So I'm going to go ahead and draw those in red here and here. And then I'm going to show in blue what was started off as our dienophile, which was our alkene group from the dienophile. That's what I've drawn in so far. We had a double bond there. Now it's just a single bond. And asking, what is this connected to? It's connected to the 5-membered ring. So therefore, it's still going to be connected to the 5-membered ring here. So I'm going to draw my 5-membered ring. 1, 2, 3, 4, 5. Drawing my carbonyl group here and here at the appropriate locations. Don't forget that extra oxygen right over here. And voila, we are done with drawing the planar structure of this molecule where we have linked via our carbon-carbon single bond, our diene with our dienophile. Those red highlighted electron pushing arrows are what have formed the bonds here and here using my red highlighter in the final product. Our dienophile, the skeleton of that, the 5-membered ring, is still intact. We didn't do anything to completely bust that apart. Still has the carbonyl groups there, and so that's what I'm showing in blue here in our final structure. And then our alkene group that is part of the 6-membered ring ends up going right here via the electron pushing arrow shown in the highlighter. So that's what I've highlighted in yellow there, just dissecting everything. Now thinking about stereochemistry, we have created a couple of stereocenters here and here. Each of those carbons that bridge the 2 rings here and here are carbons that 4 different groups bonded to. So both of these are chiral centers. And so we need to think about what the stereochemistry would be there. And we can treat this dienophile just like we would any standard alkene and thinking about the stereochemistry of this reaction. In our starting alkene, the 2 R groups are cis to one another because they go this way and the other one goes this way. They're both going in the same direction, in other words. So the 2 groups here and here, the 2 R groups bonded to the alkene, are cis. and therefore they need to be cis here as well. And so we can show that in a couple of different ways. One is you could show a wedge coming up here and a wedge coming up here. That would be one appropriate way to go about accomplishing this. You could also show the enantiomer of that by changing the wedges to dashes. Just whatever you do, you don't want to make the trans configuration of this. So the bonds that are going to the 5-membered ring need to be in the same orientation, meaning both wedges or both dashes or both lines, because of the fact that they are cis here in the starting structure. So do keep that in mind, that even when you have these weird ring systems, you still have to pay attention to the stereochemistry, because you are creating the stereocenters here and here in this reaction.